Now, let us do another example. So, second is suppose x is binomial and theta belongs to capital theta, which is 0. Goal is to estimate theta under square error loss function. Under SEL, which stands for square error loss, L theta A, which is A minus theta whole square. So, your Xn space is same as the parametric space theta, which is the general scenario in any estimation problem. So, I consider a non-randomized estimator delta naught A given x, which is half if A is equal to half if A is equal to x by n. Find a randomized estimator that has uniformly smaller risk than delta naught, or in other words, find an estimator dominating So, let us try to see what is that would be very easy because my loss function is convex in A. So, what it says is whatever randomization was required in the first stage, you take mean of that, which would be a fixed quantity, which would be a non-randomized estimator, and that would be the required estimator. So, I need to find the mean of this distribution. So, what is the random variable yx over here? Probability yx is equal to half, which is same as probability that, so you can write down small yx, which is same as probability yx is equal to x by n. So, what is the dominating estimator? Take the mean of this random variable, because my loss function is convex. So, delta 1 x, which is a randomized estimator, is nothing but expected value of y of x. And what is expected value of y of x? Half into half 1 by 4 plus half into x by n, so x by 2n. So, this is the required estimator. So, let us try to interpret what does this estimator says. This randomized estimator says that after you have observed x, the probability is half, so which is same as tossing a coin. So, after you have observed x, toss a coin, if head turns up, you estimate theta by half. If tails turns up, which is again probability half, then you estimate theta by x by n. So, it says after you have observed x, depending on head comes or tails comes, you estimate theta by half or x by n. Now, here since loss function was convex in A, we know that I can find a non-randomized estimator which has risk smaller than this. And what is that? It says just take the mean of this distribution, which does the randomization at the first stage. And mean of that distribution we found out is this. Now, to get more insight, you can do remaining problems from the assignment. Let me do another problem which I left as an exercise. So what it says is, suppose P A L. So this is an estimation problem, is invariant under a group of transformation G. So this is given to us. With induced transformations as G bar on the parametric space and G tilde on the Xn space. On P and A. Then I had mentioned that each of G bar and G tilde are group of transformations. So try to show that G bar. So my claim is G bar is a group of transformation on P. So to show that it is a group of transformation, what are the things which you have to show? The first thing which you have to show is there is an identity map in G bar. That means there is a map E in G bar such that E of f is same as f for every f belonging to P. Then you show that it is closed under composition. That means if G1 is in G bar, sorry, G bar 1 is in G bar 2 is in G bar, then composition of G bar 1 and G bar 2 is in G bar. And finally, you have to show the existence of inverse. So let us try to do it one by one. So first, I do existence of inverse, sorry, existence of identities. Now I know that this G is a group. So there is an identity element in G. So what does that mean? There exists a E belonging to G such that E of x is same as x. Now what is the definition of G bar? G bar says that for every E belonging to G, so for any element in G there exists a G bar. So that means this implies that there exists a G bar, E bar belonging to G bar such that E bar x has distribution sorry, not E bar x, such that Ex has a distribution E bar f which belongs to f p whenever x has distribution f which belongs to p. But E of x is same as x. So this implies that this is just a definition of G bar, because what is the definition of G bar? Each element in G bar induces an element in G bar which has this property. So this E which was in G, it would induce an element in G bar, so there exists a E bar belonging to G bar. And how this element is? This element will give me the distribution of Ex which is E bar f when x has a distribution f. So that means there exists a E bar belonging to G bar such that x has distribution E bar f whenever x has distribution function f. So what does that mean? Whenever x has a distribution function f, x has a distribution function E bar f. So that means E bar f has to be same as f. And this E bar is in G bar. So there is an identity element in G bar. So let us look at closed under composition. For that, what I have to show is there exists G bar, if G bar 1 and G bar 2 are in G bar, then G bar 1 composition G bar 2 is in G bar. So let G bar 1 and G bar 2 belongs to G bar. So what does that mean? This implies that there exists a G1 belonging to G and G2 belonging to G. So G1 corresponds to G bar 1, this G2 corresponds to G bar 2, such that G1x has a distribution G bar 1 f and G2x has distribution G2 bar f whenever x has distribution function f. What does that mean? So I apply this G1 on G2. So I consider G1 2 belongs to G, because G1 is in G, G2 is in G, G is a group. So this implies that G1, G2 belongs to G. We have, what does that mean? By the definition of G, there exists a bar of G1 or G2 bar, G bar, such that G1 bar, G2 bar, F, such that G1 dot G2 x has distribution G1 dot whenever now from here, what is the distribution of G1 dot from star? Because G1 is group, so G1 dot has distribution. When x has a distribution function x, G1 has x has a G bar 1 f. So this would have G bar 1. So I leave this as an exercise. Just there is a slight subtle argument. Now these two would imply that G bar 1 dot G bar 2 f is same as G bar 1 G composition G2 whole bar f. But this we have already shown is in P, is in G bar. So that means G bar 1 composition G bar 2 is in G bar. So this implies that So very simple, because first I ensure the existence of G1 and G2 such that G1x has G bar 1f, G2x has G bar 2f, whenever this. And then from star, I could say that G1 composition G2, this would be G1 composition G2. X would have G bar 1 composition G bar 2f. So that means this and this would be the same. So that is what is coming out to be over here. Now, what is remained to show is existence of inverse. So let G bar belong to G bar. Then by definition of G bar, then there exists a G belonging to G such that Gx has distribution function G bar f whenever x has a distribution function f. Now, once you have a G is in G and G is a group, there is an inverse corresponding to this. So this implies that there exists a G inverse belonging to G such that G inverse composition G x is same as x. Now, if G inverse is in G, so there exists a G inverse bar of G inverse belonging to G bar such that x, which is G naught G inverse belongs to P whenever x belongs to P. So let me write down there exists a this says that G inverse belongs to G. Corresponding to this, there will be a G bar inverse belonging to G bar such that G inverse Gx has distribution. G inverse has corresponding to this G inverse bar composition G bar x, sorry, G bar f. So this basically implies that G inverse bar would be nothing but G bar inverse. So I've there's subtle argument which I have skipped, not got into very final details over here, but that's the main idea of the proof. So that proves the existence of inverse. Now similarly, you can prove that G tilde is also a group of transformations on the Xn space. So there are other couple of problems in assignment number 1. So I would encourage you to attempt these problems. Now let me do one or two, at least one problem based on the location invariance. Yeah. So let me. So yesterday we did a problem on the normal distribution. So suppose x1, x2, xn is IID, normal theta sigma naught square, theta belongs to capital theta, which is same as r. This is known. So there is only one parameter. goal is estimation of theta under the loss function L mu A or L theta A, which is same as W of A minus theta. And my W is a convex loss function, general convex loss function. The only condition I impose is W is even function. So that means W of minus t is same as W of t for every t belonging to R. So it covers a lot of loss functions, for example, A minus theta whole square. So that means choice is Wt is equal to t square. Mod of A minus theta. That is also, that means Wt is mod of t. So that is also satisfied. So this covers very general class of loss functions. Of course, yesterday I demonstrated how to find the minimum risk invariant estimator in this situation when W was t square. So under the squared error loss function we found it out. So find MRIE, because you see in this case MRIE makes sense because we have already seen in our theory that the risk of any location invariant estimator would be constant because here G bar acts transitively on this thing. So find MRIE under additive group of transformations. So I know the idea is very simple. If a complete sufficient statistic exists, I try to find a location invariant estimator which is a function of a complete sufficient statistic. So X bar is complete sufficient statistic. Delta naught X is X bar, is location invariant. Why? Because you can see that W naught of x1 plus c, xn plus c is nothing but mean of this. Mean of this means x1 plus c, x2 plus c. So summation I is equal to 1 to n xi plus c by n. C n times, so nc upon n becomes c only, and this becomes x bar. So x bar plus c, which is same as delta naught of x1, x2, xn plus c for any c. So delta naught is invariant. So what is MRIE? Is delta naught x bar minus u star of, here I need not put d because my x naught would be, delta naught would be independent of d. So this u star would be a constant. So where u star minimizes, generally it should have been u star d, where u star d minimizes psi c, which is expected value of W of x bar minus u d, given d is equal to d, but x bar and d are independent because due to Basu's theorem. So that is why this would be just c. And given d is equal to d will not come because conditional expectation is same as the unconditional expectation. And this is, I have to minimize risk only at theta is equal to 0 because risk is constant. So I have to find out this. Now W is very general. The only thing I know is W is even. W of minus c is same as W of c. Now if somehow I can show that psi of c is same as psi of minus c, then possibly using convexity of W, I may be able to prove that psi would be minimized at c is equal to 0. You see, as a function of c, if you look at, it is still a convex function, because if I take double derivative of c, and assuming that I can take the derivative inside, it will be w double prime of x bar minus c. So expected value of w double prime x bar minus c, and w double prime is always greater than or equal to 0 for every x, so it will always be greater than or equal to 6. So psi double prime c is nothing but expected value under theta is equal to 0 of w double prime x bar minus c, which is always greater than or equal to 0. And in fact, if it is strictly convex, then there will be a strict inequality. So this is convex. So if I can show that psi of c is same as psi of minus c, then I will be in a position to show that the minimum would be attained at c is equal to 0. So that means u star would be 0. So x bar would be the minimum risk invariant estimator. So let us try to see what is psi of minus c. Psi of minus c is same as expected value of w of x bar plus c, right? But I know my w is even. So this is same as E theta is equal to 0. W of minus x bar minus c. Now, under theta is equal to 0, x bar has distribution normal 0 1 by n, and minus x bar also has distribution normal 0 1 by n. That means x bar has the same distribution as minus x bar. And when I am taking expectation over here, it is only the distribution of minus x bar which matters. But distribution of minus x bar is same as w of x bar under theta is equal to 0, so I can replace this by E theta is equal to 0, w of x bar minus c, and which by definition is same as psi of c. So psi of c is same as psi of minus c for every c. Now note that my psi of 0 can be always be written as psi of 1 by 2 c plus 1 by 2 into minus c. My psi is convex, so psi of alpha x plus 1 minus alpha y would be less than or equal to alpha times psi x plus 1 minus alpha times psi of y. So this would always be less than or equal to alpha times psi of x, so half times psi of c plus 1 minus alpha. So alpha is half, so it is again half psi of minus c. But psi of c is same as psi of minus c, so it is half psi c plus half psi c, which is same as psi c. So what does that mean? Psi 0 is always less than or equal to psi c for every c belonging to R. That means the minimizing u star is 0. And which says that delta naught x, which is x bar, is MRI. So I would stop here. I would encourage you to do more assignment problems. I can visit some of these assignment problems further in the next lecture, but then you try to do remaining problems. So one problem which I did not do very rigorously was that G bar acts, G bar is a group of transformation. I gave the rough idea, but at two places there were subtle arguments. Arguments were simple, the only thing is you have to write down those arguments in a proper manner. Now, similar fashion you can prove that G tilde is also a group of transformation on the Xn space. So try to do those problems of your own. I may do some problems on invariance again in the next lecture, and then after that I can move to scale invariant estimation. Thank you very much.